Hello, and thank you for joining us. Today's webinar is Increasing Sample Throughput for Wear Metals Analysis. Our presenter is Manny Almeida, Technical Product Manager for ICP. We will be taking questions, so feel free to submit questions throughout, and we will address them live if time permits, or we will answer individually offline. This is being recorded and will be available within a few days. Okay, now I'm going to turn it over to our presenter, Manny Almeida.
Thanks, Shelley, and welcome to everyone. Thank you for taking the time to attend our webinar today. The subject of the webinar is increasing sample throughput for wear metals analysis. This is a fairly popular application by ICP OES. Wear metal analysis or fluid analysis is done by a number of different types of organizations, heavy equipment operators, the military, transportation, railroads, utilities, all use wear metal analysis to prevent problems with equipment as they're being used. So it's a very important application of ICP. So let's start the webinar. First of all, I am with Teledyne Leeman Labs. We have been manufacturing ICPs for over 35 years. We are manufactured in the United States. All our instruments are built in Lincoln, Nebraska. Leeman has had a number of firsts in its history. We were the first to use a shell optics in ICP, which is now by far the dominant optical system used in ICP worldwide. We were the first to introduce a benchtop, which was the plasma spec, which is the instrument on the upper left column there. It was introduced in 1982. And we were the first to use increased size on the solid state detectors with the CID detector, and now with our own design, our CMOS detector technology, which is one of the largest detector formats available in the industry. And the list there shows the ICPs when they were manufactured. The ones in green were PMT based. We no longer manufacture those. The others, blue, are using the solid state detector. Okay. Wear metals or fluid analysis is done as a preventative maintenance aim. Oils, engine oils, transmission oils, any fluid that's in a vehicle can be monitored for the presence of particles which are deposited from the components that they're designed to protect. So as the engines run, transmissions run, metals particles are generated, and it's the goal of wear metal analysis to determine these concentrations. It's part of normal wear of a component, right? By periodically analyzing the oil, you can predict component failure based on the rate of increase of different metals, depending on what component is being analyzed. So by measuring this and applying trend analysis, we can prevent expensive breakdowns of equipment and loss of the capability of moving dirt, digging holes, or whatever it may be, and will increase the life of the equipment. Another aspect is fluid analysis can also be used to determine the concentration of additive elements to actually determine what the health of the oil is. Once the additive element concentrations become depleted, then the oil is no longer serving its best function and needs to be replaced. Okay. So in this particular webinar, we're going to talk about some equipment that is manufactured by our company, Teledyne Advanced Chemistry Systems, which is composed of, in this case, Teledyne CTAC and Teledyne Leeman Labs. All the data that we are going to look at was generated on the Prodigy Plus ICP. We use the OIL 7400 auto sampler, and the webinar will be two parts. The first part will feature the Prodigy Plus and the OILS auto sampler, and the second part will feature all three, where we add the AS Express to the data collection. So these are, so just introduce the Prodigy Plus. It's a optical system, can cover from 165 up to 1100 nanometers. It's available as an axial, radial, or dual view system. In this particular application, and for oils in general, we recommend the radial view. Has a low flow torch, low flow argon consumption, free running generators. One feature of the Prodigy Plus is its halogen capability, which sets it apart from most other ICPs, and also uses a CMOS array detector, which is the modern detector. We also manufacture the Prodigy 7 ICP, which is very similar to the Prodigy Plus, does not have the halogen capability, a little bit smaller form factor. The data was collected on the Prodigy Plus, but a Prodigy 7 is equally as capable in this particular application. We use the Prodigy Plus because it was a radial view system that we had, but the sample introduction part of the instrument and the software that runs these instruments are identical. The main difference is the optical system. The OES 7400 homogeneous auto sampler. This auto sampler has the ability to mix samples before they are analyzed, particularly for oils. That's advantageous because if they sit for a long time, you can get some separation, particularly when the oils are really heavy and you have a really long analysis time, and it may be hours before a particular sample is analyzed. So this auto sampler has a probe and a mixing paddle that can mix that sample up. And there's some video, we'll show you that in a second. It also has a stainless steel probe, which just a little image popped up in the middle there, that prevents crud, for lack of a better term, that may be in the oil from plugging up the auto sampler. This is a really nice feature, the way this operates. So generally anything that can fit through those little holes will fit through the pump tubing and fit through the nebulizer, and we'll talk about that. It also is available with a carbon fiber probe, so you can do aqueous samples, and that would be for people who want to do coolants. And the other advantage of this auto sampler is it has a dual rinse station and two separate peristaltic pumps, one to run organics, say with kerosene as the solvent, and one to run coolants in aqueous mode. Rather than having to change out all the tubing, you can simply move the rinse station and the auto sampler automatically detects the location and turns on the appropriate peristaltic pump. Has a drip cup, prevents samples from contaminating each other. And in this case, it's set up with 10 standard positions with 50 ml vials and 60 position racks. So we'll take a look at the auto sampler in operation. So here's the example where the first sample is being stirred. On the end where there's no sample to be stirred, the probe does, the paddle does not spin, so it's not spewing oil all over. Here is the drip cup. This prevents oil from the probe from one sample or standard or a check standard from contaminating any other position. And here is an example of the front paddle where the icon or the little finger is from the mouse. That's the paddle, and that spins and stirs that up. And here's the movement of the rinse station. You can see the upper right hand, the light will change when the location changes so that it's now ready to go for the alternate matrix. And you can see the two separate peristaltic pumps with Viton on one pump and Santoprene, I believe, as a second pump. So that's the performance of the operation of the OES 7400. Okay. For wear metals analysis, typically the most common sample prep by far is solvent dilution. Typically samples are diluted by 1 to 10. That way any issues of viscosity are minimized. The oils coming in to be analyzed can vary. You can have engine oils, final drive oils, transmission fluids, hydraulic fluids can all be mixed in one run. So by doing a 1 to 10 dilution, that will get rid of most of the issues that you might have with viscosity. On the right-hand side are some typical solvents that are used. By far, the most common solvent for the oils for wear metals is kerosene. Some of the others can be used depending on, some oils are actually better with xylene, but by far most people use kerosene. So in this case, we use kerosene. It is possible to also automate the sample preparation stage with the APS 1650 that allows people to put on a bunch of oil samples, and then they get diluted and put into the smaller test tubes, and then that rack goes right from the AP 1650 right into the oils 7400, so minimizing the amount of sample handling that the individual operator has to do. We'll next just take a look at sample introduction. In that case, that consists of the nebulizer, the spray chamber, the torch, and the pump tubing. So this is for someone that may not be familiar with wear metals or analysis of organic type samples. This will just be a little bit of a background for them, right? For oils application, we've always used the V-groove nebulizer, and so this nebulizer consists of a sample tube that delivers liquid onto a groove. Within the groove, there's a small hole which is located roughly right in this location. So a little bit right where the laser pointer is, where there's a line for the argon. So the sample is pumped, drips through this hole, drips down through the V groove, and is aspirated. It's a very relatively large sample orifice there, so relatively large particles can pass through without causing any issue. This particular nebulizer is designed to run organic solutions only. V-groove nebulizers are also used for high levels of dissolved solids or for HF type solutions. This nebulizer is not designed for it to use aqueous samples at all. Performance is not particularly good, particularly because of the surface tension of the aqueous solution. So for a coolant analysis, we would switch the nebulizer to another type, one of the concentric nebs is probably. Okay. Second piece is the cyclonic spray chamber. These are really popular spray chambers. Separates the drop spice centrifugal force. They're very sensitive because of the smaller size, and what's the biggest advantage is the small volume for fast washout, so that you don't have cross-contamination between samples or standards and check standards. For organic applications, models that have this baffle on the inside are best. That reduces out some of the material that's being aspirated from getting up into the torch. Right. And the torch itself, for organics, we said earlier, the radial view is what is preferred. Both the Prodigy Plus and the Prodigy 7 use demountable torches, and that allows you to change the injector bore. For organic solutions and wear metals, typically people will use the 1.1 millimeter, the most narrow, again, reducing the amount of material that gets up into the torch. And there are others that are used for coolant. We would probably go to the 2.5 or maybe even the 1.5, depending. There's some different sizes available. People have certain favorites. So for this particular study, we use the 1.1 millimeter injector for all samples. And then finally, the pump tubing. Typically, you replace the pump tubing. The PVC that's used for aqueous is not suitable. The kerosene will cause it to swell up and it won't pump. So we use Solvent Flex, which is the tubing that has the yellow coloring to it. That works for kerosene very, very well. For some other organic solvents, there are some other type pieces of pump tubing materials that are available if you wish to use those. Okay. Plasma parameters. Because of the higher nebulization efficiency you get with solvents, you got to change the conditions a little bit compared to what you do for aqueous analysis. So in this case, you're going to set the conditions. You want to maintain plasma stability. You want to prevent carbon formation. So it means you have that's sort of dependent on position and gas flow. And you want to be able to maintain acceptable performance. So for the plasma parameters, they typically will be somewhere within this range. The RF power is relatively narrow. We typically don't run more than 1.2 for organics. Occasionally, somebody might run 1.3 and maybe 1.4, but I typically will never run more than 1.2. That seems to be enough. Coolant flow can vary anywhere from the low end of 12 up to a maximum of 18. Again, it depends on the samples and on the solvent that you're using. I tend to go a little bit higher on the coolant flow than others might. I definitely want to prevent any problems with carboning of the torch, but I also want to prevent any issues with low flow torches that could cause them to melt. So I tend to run them a little bit higher than what others do. Auxiliary flow is to keep the plasma from causing carbon on the injector and on the intermediate or auxiliary tube. I tend to run this a little higher. I keep my torch higher in the coil than other people might, and I turn up the auxiliary flow to push the plasma away from the end. In this particular study we did, the instrument ran pretty much for 8 hours a day for a couple of weeks, and there was no carbon buildup with the setup the way we had it. The net pressure will depend on whether the solvent, the injector ID, and the nebulizer that you're using, and the sample uptake rate will depend on the solvent and on the pump tubing diameter. So we'll take a look at what the conditions are in a bit. Then what we do is we set the nebulizer pressure. So the green bullet, which is this little finger that's coming up, is just slightly above that coil, and it's up slightly above, doesn't show up all that well. And then once we have the pressure set, we optimize the view position by running a 10 ppm iron solution, or one of the standards, at the 259 nanometer wavelength line, and that sets the observation height for the analysis. Okay. So the intent of the study was, a couple of years ago, with the Prodigy Plus, we introduced a wear metals application note that had a sample analysis time of just under 2 minutes per sample. And no particular effort was made to run at high speed. It was just an application, and it was run like would be a normal lab application, where we had a long integration time, an uptake time. So we had somebody request, would it be possible to try and reduce that analysis time to be 1 minute or less, right? 1 minute was really the goal that they wanted, but they wanted to maintain the accuracy and stability of the 2 minute analysis sample time. So that was the point. That is the point of the work that we did to try and increase that time. And we were fairly confident we could easily go under the 2 minutes, but we went ahead and we decided to go ahead and do it without any modifications, using just software, and then to use some hardware. So there were two approaches: one that used the software features that are currently resident in the ICP software SALSA, which runs the Prodigy 7 and the Prodigy Plus, as well as both the older models, Prodigy and Prodigy XP, that software can go back. So the first is to use some software features to reduce the time, and then the second is to bring in the AS Express, which will increase, give us an increase over and above what we saw with just the software. So the first approach is a software approach and is fairly straightforward, right? So the software, in the 2 minute per sample one, the peristaltic pump speed is never changed. We had 50-second uptakes and 20-something second rinses. So what we were going to do with the software approach is to try and minimize all that. We also minimize all the lengths of all the tubing, so we try and reduce the length of the tubing from the auto sampler up into the nebulizer as much as possible. So during the software approach, what we do is we increase the peristaltic pump speed during the sample uptake. There's the ability to change that. We ran this one at approximately 85 RPM. Maximum is 200 RPM. So if we wanted to increase the speed even more, we could do that by increasing the speed of the pump on uptake. We also have what's called the quick rinse technology. And basically what this does is, once you have the entire sample line filled, going to the nebulizer, you can move the probe at that time, can go back to the rinse and begin rinsing, because we're only using two second integration times for 4 seconds of integration, and we have a pump tubing or auto sampler tubing filled that can take about 20 or 30 seconds to empty out, so we have more than enough. So what we do is we send the auto sampler probe back to the rinse, and we begin the rinsing while we're running the sample. So that, again, that shaves off a few more seconds So you can see the settings there on the right-hand side of the screen. Any ICP, Teledyne ICP that runs version 5 or later of this software can do this. It can be applied for aqueous samples. So we've done this with, say, soil samples for high-speed analysis of soil samples. We also have the ability to skip the rinse, which we don't do because of the differences in the wear metal samples. Could be high concentrations, low concentration. But in some soil samples where everything is relatively the same concentration, we can even skip the rinse, increasing the sample even more. So by doing all these particular changes, we were able to reduce the time to under a minute and comfortably at 50 seconds a sample. So then what we wanted to do was to make sure that we still maintain the accuracy and the stability of the previous 2-minute samples. So here are the plasma parameters for the first set of data and also for the second set. So the coolant gas was set to 14, so a little bit above the 12 that I talked about earlier. The auxiliary gas, I run a little bit higher. That way I put the torch a little higher in the coil, and I use the auxiliary gas to push the discharge away from the end of the torch. The nebulizer pressure is 25 psi, and that's related to the 1.1 millimeter injector. We can go to a little bit lower pressure, and the RF power, or the forward power, is 1.2 kilowatts, as we said. All right. Other method parameters that we use, so because we're increasing the speed, we can take the sample uptake time from what was 50 seconds in the original application and reduce that to 20 seconds by increasing the speed of the pump during uptake. If we increased it more, then that sample uptake time can be shortened even more. Right? We're going to do 2 replicates of 2-second integrations. Rinse time was set to 25 seconds, and again, that is 25 seconds that is concurrent with some of the analysis time, so we're saving a little bit time there. The normal pump rate when we're making analytical measurements is 25 RPM. The fast pump was increased. The fast pump was increased to 85 RPM. While we're running the samples, we have a QC sample run, the QC standard run every 12 samples, basically at the end of every row. And to be able to continue would be plus or minus 10%. That's pretty typical. If there's a failure, we recalibrate and rerun the samples from the last successful QC. And the uptake tubing was black tab, solvent flex for the uptake, which is 0.030 millimeters, and red tab, which is 0.045 for the drain. The wavelengths used for analysis are shown on this slide. These are pretty typical for wear metal analysis. So there's no great surprises there. These are the wavelengths that we use in the original application note. Right. Sample preparation and calibration. So we said earlier, all the samples are going to be diluted 1 to 10 with kerosene. We prepare calibration standards for all the elements at 5, 25, and 50 ppm by diluting 900 ppm. VHG V23, which is a product from LGC standards, is what we use. Additive elements are present at generally much higher or can be present at much higher concentration. So there's a separate metal additive standard, MA-5, that we use to calibrate up to 200 and 500 ppm. And to minimize any viscosity differences, we use blank oil in each standard to make sure so that the final oil concentration is 10%, which matches the 1 to 10 dilution of the samples. Okay. We also prepared some QC standards, both a number of QC standards at 15 and 25 ppm for all elements, and a higher one for the QC standards for the additive elements. We really monitored the 25 ppm the most. We did that every 12, so we ran that roughly 10 times during the analysis. And then for accuracy, so the QC will sort of display or demonstrate what the stability is. And then accuracy, there are some performance testing oils also available from LGC standards for both all the elements done by the wear metal technique, as well as the additive elements. So we prepared those and ran those after the calibration and check standards passed. We went ahead and ran these certified standards. So just typical calibration data. So here's the calibration for the iron 259 line. Calibration anywhere from 0 to 50 ppm. You can see the data's the very linear calibration curve. Very good precision, even though we have a relatively short integration time, 2 seconds, from 0.3 to 0.9%. All data collection is done in a 5 by 29 pixel subarray, which we see down in here. So it's 5 rows of pixels tall, 29 pixels wide. The analytical peak is measured in this green area. Background correction points are done under those where those blue rectangles are. And we used a 2-second integration in that, again, to improve the sample. So here are the results of the first certified standard. So we can see the measured numbers and the certified numbers, and then also the percent recoveries. So compared to what the certified value is, we're within 10% for everything, but a little better than that for most elements, which is what we would expect. We've gone and we've matrix matched our standards with the base oil, so we have a very, very good match to the samples that are in there. So this is good. This is for all the elements, so these generally have various concentrations. And there is also a sample for the really high concentration elements or the additive elements. So we can see those recoveries are again, also right around 100%, which is what we expect. So we've been able to show that, even though we're increased the speed and we're doing some things with the pump and everything, there's really no effect on accuracy, which is what you would expect. What we're really trying to do is not much changes during analysis. What we're trying to do is change things that sort of waste time before the analysis and after the analysis with the uptake and rinse. Once the instrument is running, it's running normal, except we did reduce the integration time. But again, this is a simultaneous instrument, so the peak is measured and the background correction points are measured at the same time. So even with that short integration time, all the measurements being made at the same time really keeps the precision within really tight limits. Okay. So we can see the recoveries there. Excellent. Then what we do is monitor the intensities of the stability of the check standard throughout the run. So this is a sort of a compilation of the descriptive statistics of all the check standards that were run during this analysis, roughly about 10. So we ran it every 12 samples. We had 10 oil samples that we ran, and we ran each one of those 10 times. So we had 100 samples for oil of unknown samples that we received from an oil lab, courtesy of an oil lab. So we ran every 12. We ran every 12 samples. This 25 ppm check standard. And we can see the overall recovery again is very, very close to what the theoretical value is showing. There was, even though we were running different samples, we didn't have any. There was no drift, and just also there was no updates. So we did no optics update during the run. There's no slope or intercept updates of the calibration curve, and no internal standard. So the instrument shows it has really quite good stability. Right. All right. There we go. And then here's the check standard for the high end additive elements, also showing the same type of stability. So the check standard that would require a recalibration and rerun of any samples, which is part of, there's no, if to increase the speed, you wind up hurting your stability and you're rerunning samples, well, then you're not really getting the benefit of going faster. So if you want to get higher sample throughput, reduce your analysis costs, use argon consumption. You want the easiest way to do that is to go faster and to make sure that you still maintain your analytical quality. And so we had 10 samples, and so I'll just report comparison on one. So we had the results from the oil lab and the results that we were able to obtain with our results. So if you look at that, you can see that the results between what we did in the lab at the higher speed and the oil analysis lab are really quite comparable, considering that these were done in very relatively large time interval, and also with different standards and other aspects. So we were able to match what the standard, what the results from the oil lab are fairly well. Anything with zeros, basically those are not detected. And some of the other elements like the phosphorus, you can see the phosphorus, the zinc, and the calcium numbers are high. Those are additive elements, so we would expect those to be high. So the data looks very good. So we're really quite happy with the results of just using software features that are currently in the system to increase sample throughput. All right. Then the second approach was a hardware approach. And this is using the Asx Express plus Rapid Sample Introduction System. And so this is a valve system that can basically eliminate the rinse and most of the sample uptake time by switching the valve. And we'll go through how that works. And by adding this, then we were able to reduce the analysis time to just over 30 seconds. So 31 seconds of analysis time for the two replicates. Okay. So how does the valve system work? So traditional sample introduction system, we have the auto sampler, and the peristaltic pump takes the solution from the auto sampler through the peristaltic pump tubing up into the neb, and then up into the spray chamber. So this is slow because now we have this entire line that we have to worry about clearing between samples to minimize any sample carryover, any cross-contamination of from one sample to the next because it hasn't rinsed out. The Asx approach is a little bit different. So what we have in this, so here's the Asx Express. There's a vacuum pump inside this module, and we'll look at the module in a minute. And then what happens is, so when the sample is being loaded, the peristaltic pump is essentially bypassing where the sample is and going directly to the nebulizer. So there's a reservoir, in this case of kerosene, which is feeding this. And when the instrument is not running samples or not analyzing, this is what it's doing. To run a sample, the peristaltic or the vacuum pump turns on, and that basically sucks the sample and fills up a sample loop, which is right here. And we'll show you one in detail in a second. And then that goes to the vacuum pump, then it goes out to waste, and that fills up this tube sample loop very quickly. In this particular example, since we only had two 2-second integrations, I used a 1 mil sample loop. There are larger sample loops for applications where the integration time can't be short, and you may have 3 30-second integration times, but you can still eliminate your uptake and rinse cycles and minimize the amount of time wasted for that. Then once the loop has been loaded, then the valve switches, and then now the peristaltic pump with the carrier solution pushes the sample from the loop into the nebulizer to be analyzed. And if you notice, with this setup, the sample never touches the pump tubing. And pump tubing is always one source of carryover because some elements stick to pump tubing more than others do. So it's a really nice feature to be able to eliminate that. And filling up the loop is very fast. Just a couple of seconds, and we'll see that in a second. So if you look at the Asx Express, and you break it down, so here's the the 6-port valve system, the peristyle vacuum pump, and here's an example of a sample loop right there, and that looks like a 1 mil sample loop, and that's roughly the size of the sample loop that we used in this one. So it's a roughly 1 mil. So those are the components of it. So here's an example of, now this is not from this particular data, but it's simple that I have. So it goes in, vacuum pump turns on, it's now filling the loop, and we'll see that. So here is the loop being filled. You can see the sample, the oil sample in there. Vacuum pump is now pulling samples through the auto sampler probe, and the analysis is beginning. I don't know how well this shows up, but you can see the brown color of the oil solution is slowly going away as the carrier solution is now pushing the sample through there. Now, this is a much bigger loop than 1 mil. I wanted to be able to just show you the, it was 1 mil, it filled very quickly, it was hard to see. So now it's now rinsing and now fills the loop again. You can see how fast that loop fills. And then once it switches, then the carrier solution pushes that into the nebulizer, and the samples are measured. And everything is what the sample touches. Every piece of tubing has Teflon in it, so we don't have the PVC or the coating on the PVC causing carryover between samples. Teflon is definitely better than pump tubing. Okay, this slide shows the parameters for the Asx Express. So we're using the 1 mil sample loop. So the loop load isn't very long, so it's just a couple of seconds and another couple of seconds of equalization delay to sort of everything equilibrate. With the oil 7400, you can also put in a delay for the stir, but we didn't need to use that. After the sample has been loaded on and we go to rinse, then there's the probe is evacuated for 1 second, then we rinse it for a couple of seconds, 2 seconds, and then there's a rinse station fill that makes sure that the rinse station always has solvent in it. Okay. And then if we look at the ICP software settings, we now turn this, so there's no rinse from the ice as far as the ICP software is concerned, and the uptake time is 15 seconds. So it's really the uptake time that sort of covers for all the things that are going on in the background. So if you need a little bit more time, you can increase the uptake time or you can decrease it, and that will sort of control what the overall speed is going to be. So we found that in this case, with this setting, the pump speed at 13 seconds was enough to be able to get everything done, so that when we started running samples, the sample in the spray chamber had been equilibrated and everything was ready to roll. Okay. So again, we did the check with the certified standards. I won't present that data again because it was pretty much the same, but even the check standard data, the stability, again, was comparable to what we had earlier. Again, there were no check standard failures. Because of the higher speed with this approach with the Asx Express, we actually ran more samples in the same amount of time. So in this case, this was the sum of 15 readings of the check standard. And you can see overall over the 2 hours or so, or 2.5 hours, that the RSD of the standards, the descriptive statistics, everything was less than 2% from there. So stability is quite good. Accuracy was the same as it was in the standard analysis. Right. Again, long-term data for sample number 1 that we did, there were 10, but we just present this, and this allows us to compare the long-term mean for the data with the Asx Express compared to the long-term mean for the software approach. And the time difference between these sets of samples was probably about a month. One was before Christmas and one was after Christmas. So when we got back, so the data compare very, very well with the original oil lab results and with the first run where we used just software features to increase the speed. And now we've gone to the sort of the maximum speed we can go, easily, and we can see that the accuracy and stability compared to the original data is quite good. So in conclusion, so this study shows that we can use the Prodigy Plus to perform high-speed wear metal analysis at pretty high, relatively high sample throughputs. The first approach, we use basically the standard ICP configuration with salsa software, and we modify the software so that we increase the pump speed during the uptake, fast uptake, and we use the rinse technology, which goes to the rinse while the sample's being analyzed. So we're rinsing and running samples at exactly the same time. So we could go a little bit faster if we wanted to go faster. We only set it to 85 RPM, but can go as high as 200 RPM. And that can bring the sample uptake down to really, really short period of time, maybe even 10 seconds or so. Again, the goal was to be less than a minute, so we didn't really explore how much lower we could go analysis time. Second approach used the AS Express, and that resulted in a sample analysis time of about 31 seconds, right? So those time savings achieved because we eliminate the rinse time, though we are rinsing, but again, it's being done during the analysis while the sample is being pushed into the nebulizer with the carrier solution. And one other advantage is that the sample never touches the peristaltic pump tubing. Once the sample is filled, the loop, the peristaltic pump pushes it through, so the sample doesn't touch that, so we don't get carryover from samples that have very, very high sample concentrations, say very high additive elements, or are more viscous because they're a heavier weight. Okay. And again, the other factor is that everything is Teflon tubing, so things don't stick to it anywhere near as much as you would on peristaltic pump tubing. So it clears much faster and reduces the carryover much more easily. And that brings us to the end of the webinar. And if there are any questions, we will answer them now.
Okay, I think we're running a little short on time, so we are going to go ahead and close out, and any questions that were submitted will be addressed offline. Thanks for attending.